The cross-section of all beams is the same, 200 millimeters by 125 millimeters. The simply supported span is 2.4 meters, and load is applied at 2 points, each 300 millimeters from mid-span. For an isotropic beam, that's a beam composed of a single material, under a central load, the top half of the beam above the neutral axis is in compression, and the lower half in tension. Corresponding strain distributions can be seen here. In a reinforced concrete beam, it may be assumed that concrete has a negligible tensile strength, and that the reinforcing steel carries all the tensile stress in bending. We look now at the strain and stress distributions of a beam under increasingly high loads. Approaching collapse, the steel begins to yield, and greater stress has to be carried by the concrete in compression. Correspondingly, the neutral axis moves upwards, an effect which becomes more pronounced with small areas of tensile reinforcement. The reinforcement is formed into a cage. The strength of the cubes is about 50 newtons per square millimetre, and this figure is used to calculate the expected failure load of the beams. The first beam to be tested has no reinforcement. Obviously, it will fail under a small load and with little warning, and the strains will be small. The load is applied and gradually increased. The second beam has a little reinforcement. Regular readings with the DMEC gauge show considerable change in compressive and tensile strains. With small reinforcement, there is likely to be a greater change in the neutral axis. As the load increases, so does the deflection, and cracks soon appear. When the load reaches about 11 kilonewtons, the deflection gauge is removed so that it won't be damaged when the beam fails. Failure itself occurs at 12.9 kilonewtons and results in very wide cracking, although there is no brittle collapse. The next beam, beam 3, is reinforced to a greater degree with the same type of steel. When the load is applied, DMEC readings show that the neutral axis rises rapidly, and there are soon plenty of cracks. Deflection is enough to warrant removing the gauge before failure occurs, although this is most in evidence at the top of the beam, in the failure of the concrete in compression. From now on, this is where all the failures will show themselves finally, unless the beam has no links. The next beam has a larger area of reinforcement, but no links. This time, when the load is applied, it can be considerably greater, but deflection is less, and when strain readings are taken, they show that there's a smaller movement of the neutral axis. Nevertheless, the deflection gauge is removed because the failure is sudden and sheer. beam 5 is the same as beam 4, but with links. After the load has been applied, cracks appear, but the failure is undramatic. It occurs more or less at the same load as beam 3, but it can be seen simply as the failure of the concrete under compression. Beam 6 has a still greater amount of reinforcement. Both this and the next example demonstrate the ability of beams to resist failure as the amount of reinforcement becomes more and more overwhelming. This beam reaches its final load with very little cracking underneath. When it is taken beyond failure, we can see how one of the links has been sheared by the considerable load applied, 74 kilonewtons. Again, the results show a pattern: greater reinforcement, less deflection, greater load. The last beam has more reinforcement than any of the others. When the load reaches 73 kilonewtons, failure occurs, but it shows itself only in a very slight crumbling of the concrete on top of the beam. This beam is over-reinforced with more steel than the strength of the concrete warrants. It reminds us that if we wish to raise the capacity of the beam to carry more load and bending moment, steel should be incorporated into the compressive zone of the concrete.